You know, in today's world, a crime scene isn't always a physical place with yellow tape. A lot of the time, it's a hard drive, a smartphone, or even a server somewhere out in the cloud. So today, we're cracking the code on digital forensics to see just how investigators follow those digital breadcrumbs to solve a case.
All right, so here's our roadmap for this investigation. We're going to start with the basics, what digital forensics even is. Then we'll peel back the layers of how digital evidence is structured. After that, we'll get our hands dirty and look at the actual tools investigators use, and we'll wrap up by tackling the huge new challenges that the cloud brings to the table. So, first things first, what are we really talking about when we say digital forensics?
Well, this is the core question, right? Digital forensics is the science that answers it. It's all about using highly specialized tools to analyze digital information without changing a single byte. And that's the golden rule. You have to preserve the evidence exactly as you found it, creating a perfect, court-admissible snapshot of that data. At the heart of all this is something called media analysis. Investigators are basically digital detectives, looking for the story that's hidden in the data. They're identifying, extracting, and analyzing everything. And I mean everything. The files you can see, the files you've deleted, and even the files someone tried really hard to hide. Now, you can't just jump into a hard drive and start poking around randomly. It's way too complex. To find evidence, you need a map, and investigators use a conceptual map called the File System Abstraction Model. The best way to think of it is like a digital onion. You gotta peel it back, layer by logical layer. Hey, if you have a networking background, this might feel a little familiar, kind of like the OSI model. It just breaks a super complex system down into manageable, logical layers. It all starts with the physical disk itself, which gets partitioned into what we call volumes. A single disk can have multiple volumes, just like a big filing cabinet has different drawers for different things. So here are those layers of our onion. We start at the bottom with the physical disk. That disk is broken up into volumes. Each volume is governed by a file system. Think of it as the rulebook for how data is stored. The actual data lives in tiny chunks called data units. And then you get to the really juicy part, the metadata, which is data about the data. And finally, sitting right on top is the file name that you and I actually see and click on. Okay, so we have our map. Now what? Well, now we need the tools to actually go exploring. And one of the most powerful open-source toolkits out there for this job is called the Sleuth Kit. Let's take a look at how it works. What's so brilliant about the Sleuth Kit is the logic behind its tool names. It's actually super intuitive. Each tool has a prefix that tells you exactly which layer of that digital onion it works on. So M is for media management, which is the volume layer. FS is for the file system layer. I is for the metadata, or inode layer, and so on. It's just an incredibly organized way to tackle a huge investigation. All right, let's put these tools to work and see what they can do. We'll start at the volume layer. To do that, we need a command that starts with MM, and in this case, it's MMLS, which is going to list the partitions on our evidence drive. And boom, here's our first step. The output from that command shows us the partition table. We can clearly see two primary volumes, both formatted with NTFS, that's the standard Windows file system. And we know exactly where on the disk each one starts and ends. We just officially mapped out the big picture. Okay, so now we know where the volumes are. Let's pick one of them and dig a little deeper, down to that next layer, the file system itself. For this job, we're going to use the fsstat command to get the high-level stats. And just look at the clues we get here. This tells us it's an ext3 file system, which is common for Linux, and that the source OS was Linux. We can even see the exact timestamp it was last written to, January 6, 2009. This is basically the file system's birth certificate and its last known activity log all rolled into one. All right, let's keep peeling that onion. We're going down to the metadata layer. We want to know the story behind a specific file, not just the file itself. So we're going to use the istat command to pull information from its metadata structure, which is called an inode. So check this out. We're looking at the metadata for one single file. We can see its size, who owned it, and, this is the crucial part, 3 different timestamps: when it was last accessed, when its contents were last modified, and when its metadata was changed. Think about that. We haven't even opened the file, but we already know a ton about its history. And now we've reached the top layer, the one we're all familiar with, the file name. For this, we use the fls command. You can think of it like a superpowered list directory command, because it can even show us files that have been deleted. Now look closely at this output. Most of these are just normal directories. But do you see that entry with a little asterisk next to it? offs.xcino? That asterisk tells an investigator something huge. That file was deleted and its metadata pointer was reallocated. This is an absolutely critical clue. A suspect might think hitting delete makes a file vanish, but tools like this prove them wrong every time.
So that's the classic approach, right? You get the hard drive, you make a perfect copy, and you analyze it layer by layer. But what happens when the hard drive isn't on a desk in front of you? What if the data is scattered across thousands of servers in data centers all over the world? Well, welcome to the new frontier, cloud forensics.
And let me tell you, the entire game changes. In traditional forensics, you seize a physical device. In the cloud, you have to ask, where even is the device? Traditionally, you create a perfect copy, an image. But how on earth do you image a live system that's being shared by hundreds of other customers? You go from a known, stable environment that you control to a totally unknown, dynamic one that's controlled by somebody else. And this new reality can be incredibly frustrating for investigators. They often find themselves hitting a brick wall. They're dealing with everything from cloud providers having no real forensic process in place to massive legal headaches when data crosses international borders. It all leads to huge delays, high costs, a ton of bureaucracy, and sometimes a flat-out reluctance from providers to even cooperate. And this isn't just a policy problem. It's a technology problem, too. Many of those incredible, well-established toolkits, like the Sleuth Kit we just looked at, were designed from the ground up for physical systems that an investigator could hold and control. They simply were not built for the virtualized, shared, and scattered environments of the cloud.
And this quote from the source material really just says it all. The industry just isn't ready. Cloud technology has raced so far ahead, but the plans, the policies, the procedures for actually investigating crimes within it have been left way behind. And that creates a massive, massive challenge. And all of this leaves us with a really critical question for the future. We've seen how methodical and how powerful digital forensics can be when you can get your hands on the device. But as more and more of our most important data moves into this new abstract world of the cloud, how is the search for truth and for justice going to keep up?